So thank you very much for coming. My name's Nick Davey. I'm a product manager with the Contrail business unit. And strangely, we've been working our way up the stack today, following the advice I've been getting my entire life, dig up. But I'm going to be looking specifically at the applications that are running on these fabrics we've built, and specifically the networks that these applications consume. I'm sure we've all seen this joke, seen this meme. What's inside the cloud? Mainly Linux servers. But there's a bunch of other stuff as well that we don't think about when we consume public cloud or application orchestrator resources. Things like networking, security, and load balancing are just kind of taken care of for us. We ask for a resource, we get a resource, and as long as we swipe our credit card in the middle, everything works as planned. But there's a whole bunch more work that we need to do if we're going to replicate that public cloud experience in private clouds. Because ultimately, the workflow that our customers, our users want is want resource, get resource. That simple. So it's up to us as engineers, as infrastructure owners, to build all of these services that the private cloud experience requires. Thankfully, when you've got the right network and right solution in place, that's not too hard. So I'm going to talk a little bit about Kubernetes today, or at least I'm going to frame a lot of the discussion around Kubernetes. This isn't meant to be yet another vendor Kubernetes talk. Like I said, I've got a couple minutes. We're right before lunch, so we'll keep this sharp. But why do I need a Kubernetes? What is it? What does it do? Kubernetes is an application orchestrator. It lets us manage containers at scale, taking care of all the complicated stuff like security, load balancing, resiliency, and reliability. That's really what we need to know for today's discussion, because what we're really interested in is the infrastructure we need to build to make this stuff successful. Specifically, that's going to be the security, the connectivity, and the load balancing that it takes to get an application live and out there and in front of our users and customers. So there's one or two things that we're going to talk about. Because we're going to talk about the network, we need to know what we're plugging into the network. And inside of Kubernetes, that thing that we're plugging in is a pod. And a pod is a group of one or more containers. All the containers inside of a pod are going to share an IP address and network namespace. So we can look at all of those containers kind of as one entity that plugs into our network. And these pods are designed to be ephemeral, which means we shouldn't be managing them or worrying about where they are. Instead, we're going to have well-known locations in our infrastructure where we access the services those pods provide. So we won't worry about the pods themselves. We'll worry about the whole set of pods that delivers our application. Those sets of pods make up a service. And a service is just a virtual IP address that front ends an application that we're going to expose to our users. Those services are going to either load balance traffic amongst multiple replicas. Those services can steer traffic to multiple services, do all kinds of fancy stuff. But all we need to worry about today is that we have a well-known endpoint, a virtual IP in our network. We need to get traffic to the right endpoints, the right destinations, and load share across all of our available copies. There's something subtle in everything that I've said, right? I keep talking about plugging stuff in, but we're talking about clouds, right? We don't plug stuff in the cloud. Or do we? Right? Because these containers, these virtual machines, they all have IP addresses. They all connect to networks. And we've just forgotten a little bit about those networks because they're inside the servers now. But that doesn't change the fact that there's a non-trivial network running inside of all of the servers that host these applications, providing all this connectivity, security, and load balancing. So breaking the number one rule of demos, I'm going to hop right to a CLI. And just to save my fingers, I've abbreviated the kube control or kubectl command. So we'll do this once, and then I'm going to switch back to K. So we're going to take a look. I've got the cheesiest multi-tier app deployed in my Kubernetes cluster here. And the only thing that I want to point out to you is we've got a whole bunch of IP addresses bumping around in a gigantic flat network. Now, it is the job of whatever networking solution you're using inside of Kubernetes to make sure these pods can talk. That's how we get microservices. And the other thing that we're going to talk a tiny bit about is those load balancer objects, right? How all of these microservices, these pods, these containers are supposed to talk to each other. So we'll just take a quick look at that infrastructure. And we'll see we've got these cluster IP addresses, which are going to be the well-known endpoints that all of our microservices communicate to. So in my super cheesy two-tier app, I've got my web front end. That's not doing much of anything right now. And I've got an app back end that does, well, a little bit more or nothing. And it's connected to a network. So what's this network that I keep talking about? What are we plugging into? Well, the network we're plugging into is Contrail. That should have been kind of obvious from the first hour and a half of this presentation, but just in case anyone missed it. Contrail is an SDN solution. We've focused a lot on fabric automation. We've shown you how we can use Contrail to derive deep analytics from a network. And another thing that we've been doing for a good long while is software-defined networking inside of hypervisors, in OpenStack, in VMware, and now in cloud-native orchestrators like Kubernetes. So inside of Kubernetes, we run a data plane on each of the nodes that all these containers are going to plug into. That's your access network. This is where everything's plugging into, enforcing your security policies, and doing your load balancing. And to make sure that we don't need to go into each one of those servers to give every container an IP or to set up every load balancer or to configure individual firewall rules, we have a centralized controller that coordinates all of the configuration and policy to all of the nodes running our application. There's a couple things we get out of that. We get a central point of control. That's pretty nifty. We get centralized management for defining rules, which eases the burden as we start scaling out these apps, right? Because the cloud is all about horizontal scale, but it can't be about horizontal burden on us operations folks either. And then finally, hinted at the big green box in the bottom, we got a bit of infrastructure to get traffic out of our cloud, because at some point, this stuff has to hit real physical networks.
Sorry, trying to understand, in the last presentation, or the one before, the controller was shown to talk netconf. Here it is XMPP.
Yeah, so we pick our poison based on what we're doing, right? So when we're communicating to network devices, we'll use protocols like netconf. When we're signaling routing protocol updates, we'll use BGP. When we're interfacing with software data planes in a public cloud or a private cloud installation, we'll use different protocols like XMPP. So Contrail has this philosophy of using the right protocol for the right use case. We're not going to force data center switch to pick up a new esoteric or proprietary protocol. Everything speaks netconf, so we're going to use netconf. In the case of software-defined networking data planes, we're going to pick a better protocol for interacting with those data planes directly. So generally there's no config plane in the servers. We'll interface directly with the data plane, programming forwarding rules and firewall rules using a protocol that we can kind of iterate on quickly.
Okay, so you're saying if you're running in the cloud, a virtual router, then you will use this?
Exactly. So we'll have an XMPP session between all of the data planes in deployment right back to the controller.
Okay. And you're using 3 types of overlays: VXLAN, MPLS over GRE, and MPLS over UDP.
Exactly, and that goes back to that kind of pick your poison, right? For interfacing with data center switches, EVPN and VXLAN is incredibly widely deployed. It's the dominant protocol. So in order to provide seamless connectivity between, say, a Kubernetes pod and a database server plugged into a QFX switch, we need to speak the same encapsulation and signaling protocols. But when we're communicating with, say, an MPLS WAN router, we don't want to have to do any sort of cross connects or protocol conversions or anything like that. So instead, we'll speak MPLS directly to those routers. Still tunneled over UDP, so it's not like all the data center gear needs to speak MPLS. The switches see UDP, the routers see MPLS, and everyone gets what they want.
So if you want to create a tunnel from the data center through the WAN, so you will need a WAN controller. It's called North Star for Juniper, correct?
Yeah, you can do a lot of funky stuff when you start combining controllers. For example, as you start bringing all those overlay tunnels out of your data center, you can use something like North Star to map a specific virtual network onto a slice running through a WAN. In that case, you're kind of popping off the UDP encapsulation of the tunnel and looking just at the MPLS label, because that's going to be the attribute that we use to map the virtual network onto that underlay slice. If you don't want to bother with any of that complexity, you can just focus on UDP, forwarding UDP across the WAN, and none of the transit routers never need to know that they're handling MPLS.
Okay. Correct. So you need an orchestrator, and if you want both controllers to coordinate, you need a layer above them, or?
It helps. I mean, this being Juniper, BGP is our default answer, right? So we can also use some well-established BGP communities to affect the same forwarding logic. So in the case of things like segment routed paths or MPLS, MPLS-TE, we can use things like color communities or other BGP extended communities to map traffic directly in Contrail onto an underlay path. That means that somebody has to go in and set up those communities in the WAN. So this is a perfect job for a controller. But if you didn't want to start plugging controllers into each other, it's trivial just to use some basic routing policies and map traffic.
So normally for data center interconnect, you will create what you said, the UDP tunnels from data center to data center, and you just prepare the WAN, one tunnel on the WAN. So no need to coordinate between the WAN and the data center, correct?
Exactly.
Okay.
And only when you want to have that kind of microscopic control of the pathing. So like say if you've got a very important virtual network that has all of your, I don't know, voice signaling applications in that, you're going to want to give that traffic a special behavior through the WAN. You can attach some BGP communities or interface with a controller and map that traffic onto the right underlay path. But for the rest of your traffic, I mean, bulk internet, backups, whatever, don't care. You can just let it go, treat it as normal UDP, and it's just IP routing all the way.
Okay, clear.
So I wanted to show one kind of important point here is that the sophistication of the networking tools that we use is really important, especially in production deployments when we really care about the applications. So when we're taking a look at things like the IP addresses allocated to containers, if you have a more simplistic set of networking tools you're using inside of your cloud-native deployments, this will be all that you get, right? Just a summary of the IP addresses allocated. But when we're using tools like Contrail, we can actually jump into the controller itself, and you guys have probably, or you folks have probably seen a bunch of interfaces with command, walkthroughs of command today. But we're going to hop into command again and take a look at how command sees our containers. So over here, if we take a look at a virtual network and the virtual ports that we have allocated, we can see the two containers that have been created, see a whole bunch of information, the tags that we've defined these containers with inside Kubernetes. But the part that we really care about is, first of all, that this is just the pod network. So this is the flat network that all the Kubernetes pods connect to, and the IP addresses that have been allocated. So we can go back to treating these cloud-native networks like they were traditional networks using the same sort of primitives and constructs that we're all used to seeing in troubleshooting. And inside of Contrail, we can treat these ports as if they were physical ports as well, doing everything from applying security filters to them, tapping and mirroring traffic, or rerouting traffic into services instances for, say, protocol inspection or delivering L7 security. The next thing I want to show you, and we're going to focus on a little, is how we move traffic around through our applications. Everybody talks about microservices. The really, really important point about microservices is that the communication between all of the modules in our software now takes place over a network. We're not using inter-process communication or pipes or any sort of other internal mechanisms inside of our software. We've got a network connecting all of the modules in our complex application. And in order to ensure that we have robust and resilient connectivity between all of the various services in our microservice, we use a set of load balancer objects to make sure that, for example, we can fail over between multiple instances of our application so that we can scale out across multiple servers and benefit from all of these cloud-native concepts. The thing is, in the public cloud, when we create our load balancer objects, we swipe our credit card, and then we get a slice of Amazon or Google or Azure's load balancer, and they all act in sort of different ways, but the result is the same. When we ask Kubernetes to create a load balancer, and we'll just take a quick look at our load balancer. So here's our load balancer object. All we've told Kubernetes here is that we want a load balancer. Nothing too fancy. This is, in essence, how we're going to request connectivity. And if we go ahead and create that load balancer. Oh, Contrail was too quick. I was hoping to see a sad little pending here that I could dwell on. Because in a public cloud, you'll see a pending message as the backend in Kubernetes goes out and provisions the specific cloud-native load balancer. In your private cloud, you'll just see that sad little pending note for a good long while. Because there has to be some sort of infrastructure that delivers that load balancer. So if we flip back to the Contrail view of things, let's see what happens to our virtual ports now that we've created a new load balancer. We should see a load balancer. There we go. I hope the zooming's working.
It is.
Okay. So what we see here is we've got the internal load balancer that Kubernetes has for our service. That's cool. We don't want to worry about that. That's the address that all the pods are going to use to talk amongst each other. We're interested in what we're going to communicate with as an external user. So we can see here that Contrail's allocated something out of our lab subnet. It's actually created a Kubernetes load balancer. And now this is going to act as the externally reachable IP address for our traffic. Now, here's the tricky part. Something needs to front-end this traffic. Where are we going to send packets to get to this address? There's been a variety of solutions proposed. Maybe we spray traffic at all of our servers and trust that our servers are going to do the right thing. That's a little bit scary for managing, for scaling, for complexity and configuration. There's other folks who have specific hardware load balancers that are going to act as your cloud-native load balancer on-prem. Getting better, that's, I think, the right direction, right? We've got infrastructure providing infrastructure services. But we here at Juniper, we think that routers should do the routing, switches should do the switching, and load balancers should do the load balancing. But in this case, I think using a router to do the load balancing, if we take a look at that external IP address that we allocated, so this 1084.32.137, and I'm going to hop over to that SDN gateway, the router that I've got at the head end of my data center. If I look at that IP address, we'll see we've actually received that from the Contrail controller. So it's originating a route, and that route is actually pointing to an overlay tunnel that connects to my Kubernetes node. And if we were to poke and prod that tunnel a little bit, we would see that all of the traffic destined to this IP address is going to get forwarded directly to the server hosting the container. So this gives you, using just your routers, switches, and servers in your data center, all of the infrastructure that you need to deliver a public cloud-like experience to your users, right? And if I go and I take a look at the cheesiest microservice app, I deleted my load balancer, so we had nothing before. And if I refresh this and give it a sec, my app should pop up. As long as Harry didn't suck all the luck out of the room. There we go. So the world's cheesiest microservice app. Doesn't tell you much, tells you where it's running, what namespace it's running in, and specifically what server is running this. And importantly, we've split the front end and the back end up, so you can see that we've got load balancing going into the application itself and in the back end. So I talked a little bit about resilience, about scalability. Why do we have all this Kubernetes stuff? Why do I have to use so much YAML, right? What does it get me? Well, what it gets us is the ability to programmatically interact with our applications. We can see, for example, with my app backend here, that I just have one container running. Maybe my cheesy microservice is now wildly popular after this demo, and I'm going to need more gas. So what I'm going to do is make more copies of my container. So I'm going to ask Kubernetes to scale my deployment. We're going to start off with the backend, and we're going to say we want, I don't know, 3 copies. I normally choose a crazy number, but I'm feeling conservative today. And we're going to watch. Kubernetes is going to go through, and it's going to create a whole bunch of containers to back this up. And if we take a look, we've allocated IPs and ports to all of those. If we flip back to Contrail, we should see a whole bunch of new containers, new IP addresses, and new ports. Cheesy microservice app. All the load balancing happens in the background, so hopefully non-trademark infringing space pig is replaced by another exciting creature.
How does the load balancer know about those new instances?
So every time, that's a great question. These load balancers, if we take a look at the tags, this is where all those tags come in. So the load balancer is configured to match on the tags that we've created here. Specifically, the load balancer is looking for any basic science I have running around with this app tag on it. So every container that gets created with that set of tags is a potential endpoint for my load balancer. And I can see that both inside Contrail. I can see that inside of Kubernetes as well by saying get endpoints. I'll see all of the containers that I've spawned up. Contrail uses 5-tuple flow-aware load balancing. So as I keep recreating these sessions to the back end, I'll see more and more non-trademark infringing puppet monsters. But I still have that one front end, right? My infrastructure is still kind of going through one source. So what I'd like to do is scale that out. And I need something to elastically scale the front end for this application. I'm going to go back to my router again. I always give up when it's right there. This time, instead of scaling out the front end, or pardon me, the back end, I'm going to scale out the front end. Same thing as the last time. We're going to create a whole bunch of pods. If we look, those are all going to be spread across all of the available nodes in the cluster. Kubernetes does this all on its own, so I don't need to worry about placing all of the containers in the right spot. It's going to, based on its load balancing algorithm, pick the best node, and it's just going to round robin in this case because it's a pretty lightly loaded cluster. So everything comes up, and now I have 3 front ends, 3 back ends, and this is the cool part. I mean, hold on, sorry, bury the lead. So again, if I refresh and check out which set of nodes and servers and pods that we're using for this, and I'll actually see if I can get 2 requests going at the same time. Maybe we'll get some cool answers. Oh, come on, still Kermit? I mean, sorry, non-trademark infringing frog monster.
Maybe I missed it, but how is Kubernetes communicating all of its containers and pods and load balancers to Contrail?
That's a great question as well. So Contrail's a modular orchestrator. I mean, you saw us fiddling around with some switches. We mess about with OpenStack. We do a bunch of Kubernetes stuff as well. And the way that we adapt to all of those orchestrators is by listening to all of the message buses or event buses that those orchestrators communicate on. So in the case of Kubernetes, we have a container called kubemanager that sits right next to the Kubernetes API server and watches all of the API endpoints that are relevant to Contrail. Things like network creates, pod creates, policy updates, load balancer updates. And every time Kubernetes is issued an API that's relevant to Contrail, we grab a copy of that and we do something with it.
I'm just wondering, can that communication be encrypted? Because it just seems like maybe you're listening on it, and an API call being passed in the clear.
Yeah, so
a copy of it, and when it's encrypted, then how do we do that?
So when the API endpoints are encrypted, we use the same TLS certificates to authenticate against the API endpoints. We have the option to cheat to win as well by putting the API listeners in the same sets of resources as the API server so we can listen locally. But everything inside of Kubernetes is generally an HTTPS encrypted endpoint.
Thanks.
So yeah, sorry. Let's see if I can get something cooler to happen. Okay, since I keep drawing frog, I'll show you what I was getting really excited about because, like I was saying, this whole thing is about bringing that public cloud experience back home again, right? Having that infrastructure we have in the public cloud represented in the private cloud, and that includes all of this routing and load balancing, right? So as we scaled out our application, we created 3 copies where we had 1, which means our infrastructure needs to react to this as well. And how do routers see multiple endpoints? Well, we see multiple next hops that we start balancing over, right? So if we take a look, we've scaled out our application from 1 available server to now 3 available servers. And the router is going to do the heavy lifting to start spraying traffic in a flow-based fashion into each of the web front ends. And then once it hits Contrail, we'll start load balancing using Contrail in all of the back ends.